This is the fourth video in our course, Build a propane refrigeration loop. In this video, you will construct a propane refrigeration loop and then convert the completed simulation to a template, thereby making it available to connect and link with other simulations. This video includes the following tasks: define the properties environment, add material streams and unit operations, customize the hysys workbook, manipulate the flowsheet, create and save a template. The first step in building any simulation is defining the fluid package. Apply the knowledge acquired from the previous video to build a fluid package for the propane refrigeration loop. Create a new case and add a component list using the hysys data banks. In the component list, add just one data bank component. Add a fluid package. Select finger basin. Now you are ready to go to the simulation environment in order to start your simulation. Now let's add material streams and unit operations. Add the first material stream. Set vapor fraction to 1. Set temperature to 50 degrees centigrade. Set the mole fraction of propane to 1. The propane refrigeration loop that is to be built consists of 4 unit operations: a valve, a chiller, a compressor, and a condenser. Now, let's add a valve. Set the inlet stream. Name the outlet stream. Back to the flowsheet, add a third material stream. Set the vapor fraction to 1 and temperature to -20. The next block, the chiller, will be modeled in Aspen hysys using a heater operation. Since the heat lost by a theoretical process fluid would be recovered by the propane in the refrigeration loop, the heater operation allows us to represent the heat as energy flowing into the propane loop. Name the unit operation chiller. Set the inlet stream. Set the outlet stream. Name the energy stream. Set delta P and the duty of the chiller. Now you can see that by defining the delta P and the duty of the heater unit operation, stream 1, 2, and 3 are fully defined, and the flow rate of these streams are calculated. Now let's move to our next unit operation, the compressor. The compressor is used to increase the pressure of a gas stream. Add a compressor unit operation. Rename it to compressor. Set the inlet stream and name the outlet stream and the energy stream. Keep the adiabatic efficiency to its default value. Now let's add the last unit operation in the refrigeration loop, the condenser. The condenser will complete the propane refrigeration loop, and it is placed between the compressor and the valve. Rename it. Set the inlet stream and set the outlet stream and name the energy stream. Set the condenser delta P. Now that the loop is completed, we would like to check the power requirement of the system. To check the power of the compressor, check the duty field under the parameter tab. If you are using the SI unit, hover your mouse over the duty field to see the conversion from kilowatt to horsepower. Now to our third task, customizing the hysys workbook. Aspen hysys allows you to customize the workbook view in several different ways. You can add additional pages, change the variables that are displayed on the current page, or change the format of the values. In this task, a new workbook tab containing the stream properties, molar heat capacity, mass heat of vaporization, and mass density will be added. Open the workbook for the main flow sheet by clicking the workbook icon on the Home tab. A new tab will be added, called the Workbook tab. Click the Setup button. Under the workbook group, on the Setup view, click the Add button. You should notice that in the background, on the actual workbook view, a new tab has been added. On the new object type window that appears in the foreground, click the stream on the top of the list, then click OK. Back in the workbook setup window, ensure that this new streams object is highlighted. Using the name cell, change the name of the new tab to other purpose. After renaming the new tab, look a bit lower down to the workbook setup form. You will notice the variable group, which lists the properties to be displayed on that workbook tab. Click the delete button until all the default variables are removed. In the same variables group, click the add button to add a new variable to the tab. From the variable list, let's select molar heat capacity. Repeat the previous steps to add mass heat of vaporization and mass density. Close the setup view to return to the workbook. The workbook now contains the other purpose tab, which shows the value of molar heat capacity, mass heat of vaporization, and mass density. You can notice that no data is shown for the energy streams shell Q, com HP, conp Q. You can remove these streams from other purpose workbook tab if desired. Click the Order Hide Relief button, select the 3 energy streams and click the Hide button. Click OK to return to the workbook. Now, to the fourth task in this video, manipulating the flowsheet. The hysys flowsheet window is designed to be manipulated with the mouse and/or keyboard. In many instances, either the mouse or the keyboard can be used to perform the same function. One very important flowsheet function for which the keyboard cannot be used is the object inspection. You can perform many of the tasks and manipulations on the icon of the flowsheet by using object inspection, right-clicking the object you want to inspect. An appropriate menu is produced depending upon the icon selected, either stream, operation, column, text annotation, etc. To show the object inspection menu, for the flowsheet background, right-click on any empty space on the flowsheet. And to show the object inspection menu, for a unit operation, right-click on any unit operation. Lastly, to show the object inspection menu for a stream, right-click on the stream to show the menu. Let's try another tool of flowsheet manipulation. Click on Format, Insert, add a title for the flowsheet. Now add a workbook table including all the material streams in the simulation. Right-click in the background of the flowsheet window and select Add Workbook Table. Click on Material Streams, click on Select. Right-click on Stream 3 and choose Show Table. Right-click on the compressor operation and select Show Table. After all the tables have been added, move them to a desired location by clicking on them and dragging with the mouse. Note that by double-clicking on any stream or unit operation table, you can change the displayed variables as well as the table's overall appearance. Now to our last task in this video, creating and saving a template. A template is a complete flowsheet that has been stored to your hard disk and contains additional information pertaining to attaching the flowsheet as a sub-flowsheet operation. Typically, a template is a representative of a specific plant process or portion of a plant process. The stored template can subsequently be read from your hard disk and efficiently installed as a complete subflow sheet operation into any number of different simulation models. Templates provide a mechanism by which two or more cases can be linked together and also provide a convenient method for breaking large simulation into smaller, more easily managed portions. Before converting a case to a template, it is a good idea to make it generic so it can be integrated seamlessly into other processes. In this case, the specified chiller heat duty defines the required flow rate for pan. This should therefore be removed to make the template more generally applicable case where the chiller heat duty might be defined elsewhere. Please note that although it is better practice to make the template as generic as possible prior to saving, the current instance of a template can be altered after it has been read into another simulation. Double-click the chill Q energy stream and delete the heat flow value. Select the Customize tab in the ribbon and click the Convert to Template button. Answer yes to the first query and answer no to the second query, noting that this question pertains to the simulation case, which has .hsc extension, not to the template case, which will have a unique file extension .tpl. You can now save your template by going to File, Save As, name your template, and save it to a convenient location. Back to the flow sheet. Let's assume you are in that plant. You are not able to accurately measure or calculate the chiller duty. You do, however, know that the compressor is rated for 250 horsepower and that is running at 90% of the maximum power and 72% adiabatic efficiency. To calculate the chiller duty, you need to set the duty for the compressor at 90% of 250 horsepower, which is 225 horsepower, and the adiabatic efficiency 72. Now the new heat duty of the chiller is calculated. Let's erase the defined duty and efficiency of the compressor in the previous task, and let's redefine the chiller duty. Assuming that a local propane dealer arrives at your plant selling a propane-ethane blend, 95% propane and 5% ethane. What effect does this new composition have on the refrigeration law? First, let us recheck the compressor duty and the condenser duty and the calculated flow rate of the stream. Adding ethane to the component list then going back to the simulation environment. After that, modify the composition. Now let's recheck the compressor duty and the condenser duty and the stream flow rate. We can see that the mixture is a less efficient heat transfer medium. As you introduce ethane, the refrigerant flow will increase, and both the condensing duty and the compressor power requirement will increase to maintain the same chiller duty, which is maintained since the flow sheet is a closed-up flow, and there is no change to the energy power input at that location. This concludes this video. Thank you for watching.